Hello AP Stat students, this is Mr. Hazelhorst here with your Chapter 1 Section 2 video. In today's video we're going to talk about how we can describe distribution with numbers. So as we talk about describing distributions with numbers, we're following along in this pattern of exploratory data analysis that began with our first video. So as we think about how are we going to analyze data when we take a set of raw numbers, well, our first step will always be to create some sort of plot of your data, whether it's a dot plot, stem plot, histogram, or even a box plot that we're going to learn about later on in this video and then in future days down the road. Once we have that data plotted, we're then able to get an overall impression of what that data is showing us. So we can think SOCs here, right? Shape, outliers, center, spread. And then from that, we're going to make a decision to choose some sort of numerical summary. And what we're going to talk about today are all the different numerical summaries that we can use. And these statements that you see in this box, X bar S and the 5-number summary, we'll be able to talk about those in a little bit more detail today. So all of this fits together. It's a step in the process. Graphing your data, analyzing its SOCs, choosing a numerical summary, and that's the part that we're going to focus in on today. So the first categorical of numerical summary that we need to talk about are different measurements that we use to identify the center of a set of data. And these boil down to two main types. We're going to talk about the mean and the median, and you've probably dealt with these many times before, so this should be pretty easy. All right, the mean, sometimes we refer to that as the average value. And the symbolism that we use to represent the mean is our variable with a line over it. So that's what we see here. Now in this example, we're saying X is our set of data, but it really could be any variable. We could have Y with a bar over it. We could have Z with a bar over it. But anytime we put the bar over the variable, that's telling us that that's the mean of the data. So in this case, we're describing the mean of X. And we know that we find that value by adding all the X values together. So we can see our sigma notation here, summation notation. So we're going to add all the X values and then divide by the number of pieces of data we have. That's what N is representing. Now we have a specific rounding rule for the mean that we want to follow anytime we're calculating the mean. So if I'm working with a set of whole numbers, say your guys' test scores from our first chapter test, if I'm going to report the average of that, the mean of that value, I should always round to one more decimal place than what occurs in our data. So if we're talking about whole number test scores, then I would need to round the mean to the 10th value. Okay? So that's something that I'll expect you guys to apply as we calculate means, whether it's on a test or a quiz. The median, hopefully you guys know how to find that. Pretty simple, right? We're just going to put all the data values in order from smallest to largest, least to greatest, and then we're going to find the very middle of that set of data. That's why sometimes the median is referred to as the middle value. And typically we represent that with just a capital letter M. So these two measures are what we use to represent the center of a set of data when we're talking about a numerical summary. Now when we utilize the mean and the median, while they're trying to represent the same thing, the center of the data, they do that in different ways. And there's a good reason for that. All right? We want to use these values under different circumstances. So when we talk about a symmetric distribution, and that's the example that we see here, right? All these numbers are evenly spaced out. If we were to graph those in a bar graph or a histogram, they'd just be a nice uniform distribution. But the mean and the median would be the exact same value, right? If you calculate the mean of this set of data, right? So X bar would end up equaling 4. Now we want to follow the rounding rule of the mean, so it would be 4.0. I apologize for my handwriting on this. I'm not very good with my stylus on the iPad. The median in this problem, capital M, would also be 4. Right? So this symmetric data, we can see the mean and the median are equal. And something that's relatively symmetric, they're going to be close, not necessarily exactly correct. Now, in the second example that we have on here, all right, this would be representing a skewed distribution if we were to graph this out, right? The median, still that number 4, but if you calculate the mean in this case, the mean of this set of data would be 4.7. And that's because this data is being skewed to the higher side, right? The lower values are all centered very close to 4. right? But this 7, right, that's kind of a little ways from that center. That's skewing the data towards the right, which means the mean is going to be pulled to the right of the median. Okay? So again, we want to understand that statement that the mean is always pulled in the direction of the skew. Okay? So the mean is pulled in the direction of the skew. All right? We want to remember that statement. Okay? Now the reason for this is that the mean is sensitive to the influence of an extreme observation. Sometimes we might refer to that as an outlier. Right now, not all extreme observations are outliers, but if we have some values that are flexing an influence a little bit more, they are going to skew that mean. The median, however, is resistant to an outlier. Right? If we compare these two sets of data above, the median for both of them was 4. Right? Changing these values below the median in that second example didn't change the median at all. Right? So the median we refer to as a resistant measure, while the mean is sensitive to an outlier. So those are our measures of center, the mean and the median, and we'll use these in different situations, and we'll talk about this more over the next couple of days once we get back into class. So now let's talk about our measures of spread. We have a few more options available to us when we talk about measuring spread. And so we want to talk about each one of these real quick, and then some of them we're going to describe in a little bit more detail here in the rest of this video. The first and the most simplest measure of spread is what's known as the range, and you've probably used this in other classes before. The range just simply represents the difference between the highest and lowest value. The problem with the range is that it can be greatly influenced by outliers. So we don't really use the range a whole lot. We'll kind of comment on that from time to time, but in terms of using it to make a decision about data, that's not really going to happen. Okay? So again, the range is just kind of an overall picture of data, but nothing that really helps us out a whole lot. The second measure of spread is quartiles. And quartiles are when we take the set of data and we divide it into 4 equal groups. If you've drawn a box plot or a box and whisker diagram before, you've used quartiles in the drawing of that type of plot. And we're going to talk about that more here in just a little bit in the video. Okay? The variance and standard deviation are closely related. These two go hand in hand. There's a strong relationship between the two. All right, our variance just simply measures the spread of the data about the mean. Now, I'm not really going to worry about the formula of the variance a whole lot. When we go to calculate this in class in a couple of days, we'll actually use your graphing calculator to do this. So it's really not critical that we understand the mechanics of how to calculate it. But the key understanding that I want you to have about the variance is that it's going to compare each individual data value to the mean and find the distance that each number is from the mean. And those all play a part then in the calculation of the variance. Now, the symbolism that we're going to use for the variance is s squared, as you can see in the video here. Okay? The standard deviation, again, closely related to the variance, and you can see that within its definition. The standard deviation is just simply the positive square root of the variance. So the variance we're really not going to use a whole lot. It's something you need to know about, and you need to know its relation to the standard deviation. But the standard deviation is the more important of the two numbers. The standard deviation is something that we are going to use constantly throughout this class. And so again, I just want you to have that understanding that it's just simply the positive square root of the variance. Right? So if the variance measures the spread of the data about the mean and the standard deviation is the square root of that, that standard deviation is basically representing the same thing as well. And the symbolism that we're going to use to represent the standard deviation is just lowercase s, which again, we can see the relationship between these two values when we just compare their symbols. Right? The variance is s squared, standard deviation being the positive square root of that. Take the square root of s squared, you've got s. All right? So let's talk about the standard deviation in a little bit more detail here. Now, as we finish the video today, I don't expect you to be able to write a master's thesis about the standard deviation, but I do expect you to have just a basic understanding of what it is. And so again, that standard deviation is representing the spread of the data about the mean. All right, so we've got a couple of properties of the standard deviation that I want you to be aware of. First off, again, the standard deviation measures the spread about the mean, and so it should only be used when we choose the mean as the measure of center. Remember, we have two measures of center, the mean and the median. If we're going to choose to represent the measure of center with the median, we're not going to use the standard deviation in that same problem. All right, the standard deviation and the mean are buddies. They go everywhere together, so we want to keep that in mind. Okay. The second property says that the standard deviation is 0 when there is no spread or variability. And that's what I want you to look at the two graphs at the bottom of the screen here. All right, the graph on the left represents a dot plot of data where all 5 data values fall in the exact same location. Okay? So this would be an example of a set of data where the standard deviation would be 0 because there's no spread of the data. All the data is tightly clustered. Now, as soon as any data values begin to move away from each other, that's when the standard deviation's value increases. So that's what we see in the second graph here, right? We still have 5 data values. The average of those values, or the center, would still be in the same location as the graph on the left. But the graph on the right would have a larger standard deviation because of the two values that have now moved to the left and the right of that center. Okay? They balance out in the measure of center, but they do affect the measure of spread. And so, just like the mean, the standard deviation is also a value that is not resistant. If we have a few outliers, that can influence our standard deviation greatly. All right, so those are just a couple of properties that I want you to know about the standard deviation. And as we work with this more throughout the course of the first semester and really the entire year, you're going to begin to develop a better understanding of what the standard deviation really represents. But for now, we just want you to know some of the basics about it. The next numerical summary that I want to talk about in a little bit of detail is what we refer to as the 5-number summary. And the 5-number summary is what we're going to utilize in those situations where we decide to use the median as our measure of center. So the 5-number summary is really pretty simple. It just simply summarizes the data based on quartiles. Now remember, we mentioned that quartiles are a measure of spread. So that quartile goes along with the median in terms of representing the center and spread of data. Right, so a quartile is just simply going to divide the data into 4 equal groups. And then the 5-number summary is made up of the smallest value in a set of data, all right, what we refer to as the first quartile, the median, the third quartile, and the maximum value. Now we'll talk in the next slide about how to find Q1 and Q3. How do we find the first and third quartile? And it's pretty simple. If you know how to find the median, you can find Q1 and Q3. Now, Q1 and Q3 also combine to give us another measurement in the 5-number summary that we refer to as the interquartile range. And the interquartile range is just simply the middle 50% of a data. If you think of a box plot, the box is what represents an interquartile range, and we'll see this here in the next slide, or in a couple slides down the road. Okay, and the interquartile range is just simply representing that set of data from Q3 to Q1, or the third quartile to the first quartile. And it's very simple to find. So let's talk about how we find the 5-number summary values and also how we can use those to identify outliers. One of the most important applications of the 5-number summary is testing for outliers by using what we refer to as the 1.5 times the IQR rule. You're going to see where that name comes from in just a minute. Now remember the other day when we analyzed the SOCs of a distribution, when we got to the O step, the outlier step. At that point, identifying an outlier was a matter of our opinion, but we couldn't say for certain that it was an outlier. We just thought that it might be. Well, the 1.5 times the IQR rule gives us a definitive answer to decide whether or not a data value actually is an outlier. Okay, so again, remember, an outlier is a number that falls away from the pattern of the data. It's something extremely high or extremely low when compared to the rest. So let's take a look at this set of numbers that we have down below. And first off, let's identify the 5-number summary. Okay? Well, the minimum and the maximum value are pretty easy. All right, these numbers are already put in order for us. So we know that the minimum value in this problem would be 40. The maximum would be 99. If we were to identify the median, it's pretty simple here. The median would be made up of these two 93s, right? They would both fall in the middle. So the median of this problem would just be 93. So now we want to find Q1. Well, Q1 is really simple. Q1 is just the median of the lower half of the data. So let me switch colors here. So if we just identify or look at this first row of numbers, and we're just simply going to look at the median of those two numbers, and that will tell us what Q1 is. So Q1 is going to end up being the average of 71 and 80. So if I add those two together and divide by 2, Q1 would be 75.5. Okay, change colors again here. So then Q3 is the median of the top half of the data. So in this case, Q3 would be the average of 93 and 95. So Q3 will be 94. All right, so if we want to walk through the 1.5 times the IQR rule, it's pretty easy. We've identified Q1 and Q3, so now we need to subtract those two values to get the IQR. So 94 minus 75.5, what's that going to give us there? 18.5, I believe. So now we're going to take and we're going to multiply that value by 1.5, and that's going to give us the 1.5 times the IQR. All right, so that value gives us 27.75. All right, so then our next step is that we need to subtract this number from Q1 and Q3, and that's going to give us a range, and any number that falls outside of that range would be considered an outlier. All right, so if I take Q1 and I subtract 27.75, all right, well, we can see that number 40, will fall outside our range. So this number is then going to be an outlier. So you can see using that 1.5 times the IQR rule is a pretty simple method for identifying an outlier. Now, I mentioned before, if you've worked with with a box plot before, you've actually worked with the 5-number summary. A box plot identifies the 5 numbers that make up that 5-number summary. Right? So in this example, we've got a picture of a box plot. So this end of the whisker would be our minimum value down here. This value would make up our maximum. The line in the middle of the box would be our median, and then the box itself is representing the IQR. So the left end of it is Q1, the right end of it is Q3. Now, in this class, we're also going to work with what are known as modified box plots. And a modified box plot uses the 1.5 times the IQR rule, and it flags anything that's an outlier. Okay? So that's what we see in this picture here. And we'll show you how to create these on your graphing calculator over the course of the next couple of days. So don't stress too much over how to do this right now. So as we think about all the things that we've covered in today's video, right, what it boils down to is a comparison between two different numerical summaries. We have the option to either use the 5-number summary or the mean and the standard deviation. Right? We'll never use all of them in the same setting. We'll use one or the other. Right? Now, we want to understand what situation should we use which. Well, the 5-number summary value is going to be used when we work with a skewed distribution or a distribution with strong outliers. And then our mean and standard deviation are going to be used in situations where our distribution is symmetric. So this again stresses the importance of graphing our data first. When we plot our data in a stem plot or a dot plot or a histogram, we're able to determine whether or not that distribution is symmetric or skewed, and we can then make the appropriate decision in which numerical summary we should work with. Okay? So we want to keep that in mind, again stressing the importance of graphing our data first. To close today, I just want to share with you an example of a couple of computer printouts that we use to represent our descriptive statistics or numerical summaries. So here you can see we have a couple of different computer printouts, but I just want you to see how it gives all of those values that we've talked about today. So in the first example, you can see we're talking about this value of highway miles per gallon, but in this computer printout, we've got the mean, we've got the standard deviation. It represents or shows the variance with us, not that that matters too much. And then the rest of these values, right, the minimum Q1 the median, Q3, and the maximum, well, there's our 5-number summary. Right, so all those values are oftentimes going to be given to us in a computer printout, and we can see the same thing in the picture down below. Right, down below looks a little bit different, but the same information is given. Right, we have the mean and the standard deviation, we have the median and the rest of the values that make up the 5-number summary. Now this one also includes some values that are known as the true mean and the standard error of the mean. And these are values that we'll work with in the second semester, so don't worry about them right now. We just want to focus on the ones that apply to our numerical summaries at this point. So that brings us to the end of our Chapter 1, Section 2 video. Hopefully a lot of the material within this is new. Hopefully you've kind of covered this in various classes over the course of your mathematical career. But again, we'll take some time to break down some of this information in a little bit more detail over the next couple of days in class. So have a great day, and don't forget to complete the form below the video. We'll see you guys later. Bye.
Made with Doodlecast Pro.